Hello, everyone. My name is Jane from the Rensselaer Polytechnic Institute Engineering Ambassadors, and I'm here today to talk to you all about a new and interesting technology, thermoelectric devices. What do you think a thermoelectric device does? Thermoelectric devices convert heat or temperature difference into electricity. During this presentation, we will cover three main aspects of thermoelectric devices: why they matter, how exactly these devices work on a molecular scale, and some current and future applications of thermoelectric devices where we might see them being used in the real world. So let's first discuss the importance of thermoelectric devices. Here is the 2015 energy profile for the US. As you can see, we are heavily reliant on fossil fuels for the vast majority of our energy. This poses some serious problems, including pollution and the production of greenhouse gases, which are dangerous to humans and to the environment. Only approximately 7% of our energy comes from renewable sources. We really need to focus on expanding that 7% so that hopefully one day our energy profile will look completely different and we won't have to rely primarily on harmful and depleting fossil fuels. Hopefully in the future our energy grid will look more like this, with a main dependence on a wide variety of renewable energy sources. Renewable energy sources take many forms, including wind, solar, geothermal, hydropower, and tidal power. In fact, engineers and scientists are still discovering renewable energy sources. Did you know that thermoelectric devices produce energy renewably? Because heat and temperature differences are constantly being produced, capturing these temperature differences and converting them into electricity is a completely renewable process. I have a question for you all. What is efficiency? Engineers and scientists define efficiency as a comparison of how much work or energy is put into a system with how much work or energy you can get out of a system. If something is 100% efficient, this means that exactly the same amount of energy that was put into that system is extracted from that system in the desired form. When converting energy, we will always convert a fraction of that energy into some waste form of energy, such as heat, and only a portion of that original energy is converted into the form that we want. For example, when a certain amount of energy in the form of coal goes into a power plant and gets burned and turns turbines to produce electricity, only a fraction of the total energy put into the plant is actually converted into the form we want: electricity. Lots of that energy is lost to heat, which is a form of wasted or unused energy. Therefore, this system is not 100% efficient. Here's another example. What have you ever noticed about light bulbs when you turn them on? Can you think of the two types of energy that the electricity is converted into in a light bulb? Light bulbs convert a portion of the input electrical energy into light energy. However, light bulbs also produce a lot of heat, which again is a form of wasted energy. Therefore, this system is also not 100% efficient. When talking about these energy conversions on a global scale, the world's power continues to be generated at 30 to 40% efficiency, despite advancements to our grid system. Again, efficiency is how much energy you get out versus how much energy you put in. So overall, 30 to 40% efficiency is not a lot. Where does the rest of that energy go? Most of the wasted or lost energy is thermal energy. In fact, in 2012, humans produced 15 terawatt years of wasted energy. A terawatt year may sound like a very odd unit. We measure rates of energy consumption by watts. Therefore, energy consumption itself is measured in watts multiplied by the amount of time that the energy rate is consumed over. The best way to understand this unit is in terms of light bulbs. A standard household light bulb consumes energy at a rate of 100 watts. So 100 watt years is the amount of energy consumed by a single light bulb over the course of 1 year. 15 terawatt years of energy is approximately what it would take to power enough light bulbs to stretch from the sun to Jupiter and back for an entire year if you lined them up over that entire distance. Simply put, we could power this line of light bulbs each year just with the amount of energy we waste, and this number is only growing as our energy demands increase. Where do thermoelectric devices fit into all of this? Since thermoelectric devices use a temperature difference to convert heat into electricity, these devices can be incorporated into existing systems to make them much more efficient overall. Take our coal power plant example from earlier. We can make that power plant more efficient by using the excess heat and converting it back into electricity with thermoelectric devices. Next, let's discuss how these devices actually work. Thermoelectric devices are able to take energy from heat, or a temperature difference, and convert it into electrical energy, thereby powering an electronic appliance such as a light bulb. What's super interesting about these devices is that they can actually work in reverse as well. If we connect them to a power source, such as a battery, they convert electrical energy into a temperature difference, producing a hot and a cold side. This has unique applications for a variety of systems. These features of thermoelectric devices are made possible by bismuth telluride, a very special material that has unique electrical and material properties. It is able to perform the task of converting between the types of energy. Electricity is all about the movement of electrons inside a material. So when it comes to creating it, we need to focus on how electrons are moving in bismuth telluride. There are two types of bismuth telluride used in thermoelectric devices. The first one is called P-type, which stands for a positively doped material, which simply means that this material has less electrons in it than would naturally be found. The electrons that it does have are shown here in white. In P-type bismuth telluride, when a temperature difference is applied, the electrons will naturally move from the hot side to the cold side. The other kind of bismuth telluride is called N-type, which stands for a negatively doped material, which means that this material has more electrons than would naturally be found in it. In N-type bismuth telluride, electrons will move in the opposite direction, from cold to hot. Knowing this about N-type and P-type bismuth telluride, thermoelectric devices are developed by engineers using alternating blocks of P and N-type bismuth telluride material. These blocks of bismuth telluride are connected by strips of conductive material, like a copper wire. When a temperature difference is applied, the electrons are forced through the device, like so, creating electricity. Now that you're all experts on bismuth telluride and thermoelectric devices, we'll talk about some really cool applications of them, and where you might see these devices in the future. These applications range from cars to refrigerators and even gear on the battlefield. This technology is being used in hybrid cars to charge the battery or power the electric motor, making hybrid cars even more efficient. The engine creates a lot of excess heat, and using these devices to recapture that heat would allow the car to run more efficiently by helping to charge the car's battery as it ran. This would mean fewer trips to the gas station and more time on the road. Normal refrigerators are noisy and have a complicated series of tubes in the back of them that use a toxic and environmentally harmful refrigerant fluid in order to work. To avoid all this, we could use thermoelectric devices to make refrigerators function. Using the reverse capability of producing a hot and cold side when connected to a power source, such as an outlet, we could create a silent and completely steady-state refrigerator by encapsulating the cold side of the thermoelectric device. Thermoelectric devices can also be incorporated into the design of military gear. They could use body heat to charge and power devices the soldier might need on the field. In reverse, these thermoelectric devices could keep soldiers comfortable in hot or cold environments if we placed them inside of the uniform so that they could cool or heat the soldier using small batteries. Many different types of engineers work on thermoelectric devices and incorporate them into these various applications. Materials engineers work on discovering and manipulating the bismuth telluride in thermoelectric devices or other materials in the device, such as the ceramic coating or the conductive strips, in order to improve the function of these materials and optimize the device's reliability and efficiency. Chemical engineers innovate processes for producing high-purity materials needed for thermoelectric devices on a large scale and make these processes economically profitable and feasible. Electrical engineers are responsible for the wiring in the device, as well as analyzing and optimizing how electrons move within the material and circuit. Mechanical engineers might work to implement thermoelectric devices into mechanical applications, such as a car. Nuclear engineers will potentially use this technology in power plants to increase energy efficiency in the future. In summary, as we live on a finite planet with depleting resources, and as the world's energy demands continue to grow, it is becoming increasingly important to use the resources and energy that we do have in a responsible manner. Thermoelectric devices and the engineers that work on them can help us to produce and use our energy more efficiently in the future. Thank you for listening to our Rensselaer Polytechnic Institute Engineering Ambassadors presentation through REACH. Hi everyone, my name is Jane. I am with the RPI Engineering Ambassadors, and I'm here today to do the hands-on for you for the thermoelectric devices presentation. So thermoelectric devices, we know, can take in a heat difference, so a hot and a cold, and they can produce electricity, but they also can be hooked up to a power source and then actually produce a hot and a cold side themselves. So this is what a thermoelectric device looks like. It is a small, thin ceramic device, and it just has its kind of two leads here that we can use to attach to our power source. So in this case, we are using a battery. And so all I'm going to do is simply, just with my hands, I'm going to attach these two leads, so the positive and to the negative sides of the battery, and it doesn't matter red or black, which to which. And what I'm going to do is I'm actually just going to hold this between my fingers, and what I can feel is on one side of the device it becomes very cold, and on the other side it's becoming very warm. So here you can see for yourself that thermoelectric devices are really good at creating a heat difference or a temperature difference on a hot and a cold side just with a simple battery or a power source. So now that we've experienced that, we can move into the other part of the hands-on, which is actually testing how much electricity we can produce using a thermoelectric device. So here we have a simple circuit setup with a propeller, and this is just hooked up to our thermoelectric device here. So what we need in order to produce electricity is a heat source or a temperature difference. So I'm going to use a beaker filled with ice water. And then we know that we need a temperature difference, so in order to create that, I'm going to use some warm water. So this is just some water that I heated up using an electric kettle. So I'm just going to carefully pour this in, and it is very hot, so you want to be careful when you do this. And so here I have my hot and my cold, my temperature difference. And so next what I'm going to do is I am going to use my copper plates that I have handy, and I'm going to hook up my thermoelectric device to this setup. So to do this, I'm just sandwiching my thermoelectric device in between these two copper plates with the wires facing up. So I'm doing that here. So you're going to get kind of this upside down Y with your thermoelectric device sandwiched between those two plates again. And I'm just going to pull this all together holding a binder clip like this. And I'm going to place this one into each, into my cold and my hot source like this. And so here we're supplying our temperature difference to our thermoelectric device. We have our hot source and we have our ice water. And so because we are scientists and we want to keep all variables constant when we're doing this, because we'll also do this with some aluminum plates, what I'm going to do is I am going to, and you can see now, we are creating electricity. This thermoelectric device is creating electrical output that then is powering this fan. So what I'm doing right now is I'm just taking note of what this temperature, this hot one, water, the temperature is, so that when I do this with the aluminum, I can try to keep that constant, and I can really just measure the difference between copper and aluminum. So right now, this is reading out at about 78 degrees C, so it's pretty warm. So next what I'm going to do is I'm going to turn on my voltmeter, and this is measuring how many volts are actually being produced by this thermoelectric device. So I have this setting on direct current because the current that we're producing from this is not alternating, it's just simply direct current. So to do this, I'm going to take my black and my red, and it doesn't matter which goes to which. And I'm just going to attach these to either side of my circuit like this, and I'm going to note the voltage that's being produced. So here I see 0.47 volts are being produced by my thermoelectric device. So next, we're going to move on to using our aluminum plates, and we're going to be able to compare that to how well the copper plates did versus the aluminum. So to do this, I'm just going to disassemble, and I'm going to reattach to my aluminum plates. And you can see as I'm doing this, obviously the fan stops spinning because we're no longer producing electricity, because we no longer have a temperature difference attached to this device. So here I'm just going, just like I did with the copper, I'm going to put this in like so. So I have my hot and my cold source. I'm going to just measure this water again to make sure that we're keeping that temperature pretty constant throughout our experiment. And so as we're waiting here, this hot water, again, is transferring heat to one side of the device, while this cold water is cooling down the other side of the device. And so that's what's creating our temperature difference. And so here I see I'm getting 70 degrees C, which is a little less than last time when I was seeing 77 degrees C. So what I'm going to do to make sure that we're keeping temperature constant, I'm quickly going to refill this beaker with some fresh hot water. Going to remeasure the temperature. Sometimes these fans need a little help, they get stuck. But you can see, if you do notice, this is actually spinning at a little less of a speed than we did have with the copper. And so now I'm seeing that 78 degrees C again. So I'm able to keep temperature constant as I do this, and we're able to just look at the impact of copper versus aluminum plates on this system. So I'm going to take my voltmeter, just like before, and again, using that direct current setting, I'm going to attach to either side of my device, like this, either side of my circuit. And here I'm seeing 0.31 volts. So if you recall, that's a lot less than we were producing compared to the copper. So here we can say that the aluminum is less efficient than the copper. Since we're keeping everything else constant, we have the same energy for our system, we have the same initial input of hot and cold water, but our output is different. So this is a less efficient system overall. So the reason that it's less efficient is because copper has a higher specific heat capacity than aluminum. So what that means is that copper is better at transporting heat or retaining that heat to get to the sides of this thermoelectric device than the aluminum is. So here we measured the temperature. We know that we're working with the same temperature difference in each system. However, with this one, if we think about heat transfer and what's happening here, the aluminum gives off more of that heat as it's transferring from our beaker to the side of the device than the copper does. So the copper retains that heat and it's able to create more of a temperature difference than the aluminum is. So something else kind of interesting that we can do with this system, just to test it out and play with it a bit. So what do you think will happen if I go ahead and I switch the sides of my thermoelectric device and I change which one is hot and which one is cold. So what's happening right now is what used to be the hot side is now cooling down, and what used to be that cold side is heating up. So we can actually see that response happening with our fan here, where right now the temperature difference is 0, so we don't see any movement with this fan. And that new cold side now is cooling down, and this new hot side is heating up. So we're going to see that this fan will restart with a little bit of a nudge. There we go. So now the fan is actually moving in the opposite direction than it was before, and that's simply because we switched the circuit. We switched which side was hot, which side was cold, and kind of the direction that we're sending these electrons through the circuit. So to wrap up, thermoelectric devices are really cool. There's tons of applications for them. I hope you enjoyed our hands-on. Thank you so much for listening, and I hope you enjoyed this RPI Engineering Ambassadors presentation.